Hi, my name is Jacob Pushy, and today I'll be discussing with you an experiment titled the Fireproof Balloon. For this experiment, we were instructed to expose two balloons to a heat source, one filled simply with air and the other filled with water. I will now demonstrate that experiment to you all. So, when you expose a balloon strictly with air to a heat source, it bursts. However, when you expose a balloon filled strictly with water to a heat source, as you can see, it doesn't burst, like the one with air. And I'm going to explain to you guys exactly why that occurs. So, as you can see, the balloon filled with air bursts almost immediately, while the balloon filled with water does not burst in the same way. The water-filled balloon does not burst because the rubber does not reach a temperature sufficient for it to melt or burn. The rubber is stretched so thin that the heat is quickly transferred into the balloon. Now, with the air balloon, this heat is not readily dissipated away from the spot touching the flame, and as a result of this, the balloon melts or burns and then quickly bursts. The water, on the other hand, has a higher capacity to absorb heat than does the air. This heat is readily dissipated into the water and away from the wall of the balloon so that the rubber does not heat up enough to burn or melt. So, the difference between the temperature and heat can be understood by considering a red-hot steel pin and a large block of steel. Both of these objects are made of steel, and both can be heated up to exactly the same temperature. However, if at the exact same temperature the pin is dropped into a bucket of cold water, you may just hear a tiny hiss and there's no real change in the temperature of that bucket of water. However, if you were to take that large block of steel at the same temperature as the pin and drop it in the bucket of water, what you'll see is a rapid boil beginning in the bucket and a large hiss from the bucket as well. And it'll be much longer and much more pronounced than the previous pin. So, as you can see, the block of steel was at the same temperature but contained more heat energy. And a similar situation is occurring here in that water has an impressive capacity to store heat, much more so than air does. The term for this is called specific heat capacity. Heat is a form of energy and is measured in joules in the International System of Measurement, which we learned about in our readings this week. This system of measuring heat is based on the amount of heat required to raise the temperature of water. 1 calorie will raise the temperature of 1 gram of water by 1 degree Celsius. Interestingly enough, it only takes about an eighth as much energy to raise the temperature of 1 gram of iron by the same amount. So as you can see by this comparison, the heat capacity of water is quite impressive. One practical example of the great heat capacity of water is that it has a significant effect on weather along the coastlines. Water can retain its heat much better than sand or soil can, and for this reason, at nighttime you'll notice the ocean temperature varies only slightly while the land temperature will plummet several degrees. The heat capacity of water also makes eating hot apple pies a dangerous endeavor too. The filling of an apple pie is a large water content because apples have a large water content. The pastry has a much lower heat capacity than water and cools much more quickly than the filling. So because of this, you may touch an apple pie and it may feel cool because the pastry does, and then you go and eat it and you can be severely burned on the tongue and your roof of your mouth because the heat capacity of the filling is much higher than the pastry is. So as you can see, as explained and demonstrated in this lesson, water has an impressive specific heat capacity, and for this reason, the balloon in this example does not pop immediately like the balloon filled with air. And that is the end of my lesson for you today. Thanks.